Other phenomena also challenged classical physics in the scale of atoms. For example, in classical physics, physical quantities were considered to be continuous. But atoms showed discontinuous physical quantities. For instance, when hydrogen atoms are heated, only light of certain wavelengths is emitted. They are called lines. Balmer found 4 lines from the visible range of light from hydrogen atom. Similarly, sodium has a line spectrum, in which the yellow line is the brightest in visible range. That is why sodium shows yellow color in flame test. The line spectra of atoms cannot be explained by classical physics. Regularity was discovered in the line spectrum of hydrogen. Rydberg proposed the equation for the characteristic lines of hydrogen emission. The reciprocal of wavelength is proportional to 1 over n1 square minus 1 over n2 square. The proportionality coefficient is the Rydberg constant. n1 and n2 are positive integers. According to the value of n1, the lines are categorized into series. For example, the lines of n1 equals 1 are Lyman series. They are in the range of far ultraviolet. The lines of n1 equals 2 are Balmer series. They are in the range of visible and ultraviolet light. We will see later, such discontinuity in wavelength corresponds to discontinuity in energy. You can pause the video here to check the example by yourself. Black body radiation is another problem that classical physics cannot solve. In the 19th century, to obtain high-quality steel, the control of temperature was crucial. However, the temperature is so high in the blast furnace, so that no conventional thermometer can be used inside it. Alternatively, temperature was estimated according to the light emission from the furnace. Say, red for low temperature, while white for high temperature. But such estimation was only qualitative. To quantitatively study the emission light from a body, we should analyze its spectrum, which is the relationship between spectral radiance and frequency or wavelength. The spectral radiance is the power density per unit solid angle per unit frequency or wavelength range. Here, I show you an example of the spectra of sunlight without atmospheric absorption and sunlight at sea level. A black body is a body that does not reflect light at all. Perfect black body does not exist, but the reflection can be minimized by such a setup. A chamber is made of very black and opaque material, and it has a tiny hole on its wall. When light enters the chamber through the hole, it is heavily absorbed every time when it is reflected by the wall. Therefore, the fraction of light reflected out of the chamber through the hole is negligible. The chamber can be regarded as a black body. The radiation observed through the hole has no contribution from reflection, but is the radiation from black body. Here, I show you some spectral radiance of black body at different temperatures. There are 2 noticeable tendencies. First, the total radiance, which is the area below the curve, increases with temperature. Second, the frequency of the maximum radiance increases with temperature. This is in accordance with the color change we discussed just now. Physicists tried to explain the black body radiation with classical theories. Wien fitted the black body radiation at high frequency using his approximation. But Wien approximation failed to reproduce the black body radiation at low frequency. In the Wien approximation, pay attention to the Planck constant and the Boltzmann constant. It is the first time we see them. We will use them repeatedly in general chemistry. We can derive the Wien's displacement law from the Wien's approximation. It says the wavelength of the maximum radiance is inversely proportional to the temperature. It is also in accordance with the color change. Rayleigh and Jeans developed the Rayleigh-Jeans law. It is based on classical electromagnetics and statistical mechanics. However, Rayleigh-Jeans law is only correct at low frequency. So far, the black body radiation is unexplainable by any classical theory. Max Planck established the Planck's law, which perfectly agrees with the black body radiation in the entire frequency range. Planck himself did not understand this law at the beginning, but later, Bose and Einstein derived the same law based on Bose-Einstein statistics. It suggested that electromagnetic wave is also particles. It is one of the most important evidence of the quantum hypothesis of light. Here, I show you the Planck's law, Wien approximation and Rayleigh-Jeans law at 1000 Kelvin. Pay attention that the Planck's law reproduces the black body radiation perfectly. Wien approximation is only correct at high frequency, while Rayleigh-Jean's law is only correct at low frequency. Rayleigh-Jean's law even blows up at high frequency so that the total radiance is infinity. It is impossible. Recall that Rayleigh-Jean's law was derived based on classical theories. Therefore, the classical theory failed, not only because they do not explain black body radiation, but also because they lead to unrealistic and counterintuitive result. This is called ultraviolet catastrophe. The last phenomenon which cannot be explained by classical physics is the photoelectric effect. Philipp Lenard discovered that, when illuminate a metal with light, there is a minimum frequency, above which electrons can jump out. It cannot be explained by classical physics due to the following reason. In classical physics, light is electromagnetic wave. As electromagnetic wave, light power is proportional to the square of its amplitude, regardless of its frequency. Therefore, classical physics predicts a minimum intensity, rather than minimum frequency. The photoelectric effect marks the failure of the wave theory of light. Einstein succeeded in the theoretical explanation of photoelectric effect using the quantum hypothesis of light. In his theory, light is also particles called photons. The energy of a photon is h nu, or h bar omega, or hc divided by lambda. H bar is reduced Planck constant. Nu is the frequency. Omega is the angular frequency. C is the speed of light. Lambda is the wavelength. The energy diagram of photoelectric effect is shown below. The vertical axis is the energy of electrons. The electrons in the vacuum have certain energy. The electrons in the metal have a certain range of energies. The energies of electrons in the metal are lower than that in the vacuum. The difference between the energy in the vacuum and the highest energy in the metal is the work function. When light illuminates the metal, the energy of a photon is transferred to an electron. If the photon energy is not enough to compensate the work function, the electrons in metal are not kicked out into the vacuum. If the photon energy is greater than the work function, some of the electrons in the metal can be emitted. The extra energy is converted to the kinetic energy of the electrons. In photoelectric effect, the kinetic energy of the emitted electrons must be smaller than the difference between the photon energy and the work function of metal. You can pause the video here to check the example by yourself.